Three of you on Zoom, one on campus. Not many. Still, all right. This week is the last. It's not the last week, but it is the last content of the syllabus. All right. So whatever I cover, this will be the last thing that you need to know for this course. Next week will be revision week. So you can bring all your questions next week. I mean, you don't need, of course, you don't need to wait till next week. I mean, you can contact me 24/7, as you know, for any questions you guys have, right? Okay, and thank you for handing in quiz number 8. I will have them, well, I'll have them marked today and try to send you later today. And one more on, well, about the in-class test. Yeah, the in-class test will be next week. It will take place Thursday and Friday of next week. That is 16th and 17th of December. So it will start at 1 p.m. on the 16th. So you will be able to see the test paper or just the PDF file containing the questions of the test at 1 p.m. 16th of December, and you will have 24 hours, one full day, to answer the questions, and you should upload your answers to Blackboard by 1 p.m. on Friday, the 17th of December. There should be no excuse for not having enough time. Okay, 24 hours is a lot more than what you normally get. Okay, so please try to have your answers uploaded before 1 p.m. Friday, the 17th of December. All right, okay, so let's back to the class now. So the last topic I'm going to talk about for this course is bivariate extreme values. Now, so far, like at the very beginning of this course, I talked about univariate extremes, right? So this is just a generalization of the univariate to the bivariate case. Now, bivariate extremes arise in many different areas in real life. So I'll show you some examples. So if you look at tornadoes, which occur mostly in North America, these are caused by extreme values of humidity and wind speed, right? And if you look at droughts, mostly occurring in Africa, these are caused by extreme values of extremely low rainfall and extremely high temperature. Okay, and if you look at forest fires, again in North America mostly, also Australia, these are caused by extremely high temperatures and extremely high wind speed. I'm sure you watched these videos, so I'm just repeating. Maybe this is floods. It's more like Manchester. So this is caused by extremely high rainfall and extremely high wind speed. And these are hurricanes caused by extremely high sea temperature, rainfall, and wind speed. And finally, this is El Nino. You might have heard about this. And these are caused by extremely high sea temperature and high air pressure. All right? So the question is, in order to model these events, you need to look at extreme values of 2 or more variables, right? So how do you... So what I'm going to talk about today is how to go about modeling them. Okay, so the first thing is how to define. The first thing is how to define a bivariate extreme value, because it's not obvious. Like in the univariate case, you should given a data set, you pick the largest test or the smallest. That's the extreme value, which is obvious. But in the bivariate case, it's not so obvious because of the following, right? Suppose you have two variables, x and y, and suppose these are the data on x, is the data on y. There is no obvious definition for a bivariate extreme value, but the most common definition is this one here, right? It's a vector containing two numbers. The first number is the largest of the x's, and the second number is the largest of the y's, right? So for example, if you take this data, suppose these are the data on x, and suppose these are the data on y, right? So the largest of the x's is 8, right? The largest of the y's is 9. So the extreme value is 8, 9. You follow me? Yeah? Any questions, just use the chat room, guys, okay? But one unfortunate thing about this definition is that the vector containing 8, 9 is not an actual observation. You see? It's not an actual observation, because as you can see, the observations are -5, 3, 0, 2, 1, 9, 8, 1, and 2, 3. And 8, 9 is clearly not one of the observations. So that's the main weakness of this definition. All right, that is the bivariate extreme value may not be an actual observation of the data. Whereas in the univariate case, it must always be an observation. It is an observation, right? So that's a weakness, but nevertheless, that's how that's the most common definition. All right, so just for modeling interest, modeling the bivariate extreme value, you look at the limiting distribution of the bivariate extreme value as n goes to infinity. But as in the univariate case, we remember when we talked about the extremal types theorem in the univariate case, we looked at the limit of the scaled version of the sample maximums. So that's what I'm going to do here. So instead of looking at the limit of mn1, mn2, you're going to look at the scaled version of both. So I'm going to scale mn1 by bn, subtracting bn and dividing by an, and scale mn2 by subtracting dn and dividing by cn. All right? So this is the scaled version. Right? Hi, Veronica. So you're going to look at the joint distribution of the scaled version, and if you do the math, I'm sure you know, you've gone through this, I hope so. So you do the math, you will get this joint probability to be equal to star, which is the joint CDF of x and y at these 2 points raised to the power n. So the question is, what is the limit of star as n goes to infinity? Right? Now, you may recall I asked a similar question in the univariate case, right? And the answer was that it must be of the same type of it must be of the same type as either Gumpel or Frechet or Weibel in the you remember that, right? In the univariate ETT. But unfortunately, in the bivariate or multivariate cases, the limit, if it exists, suppose the limit is g of x, y, right? The limit, if it exists, can be uncountably infinite different forms. Can take uncountably infinite different forms, right? So that's a main drawback with bivariate extremes, bivariate extreme value theory, or multivariate extreme value theory, because the limiting distribution, which is also known as the bivariate extreme value distribution, can take uncountably infinite different forms. Okay. So let me summarize what I talked about so far. So this is what I've talked about so far. So you have data on x, y, and you define the bivariate extreme value as this, right? And then you look at the joint distribution of the scaled version of mn1 and mn2, right, which is equal to this. And you look to see if the limit exists. If the limit exists, right, if the limit exists, then it can take uncountably infinite different forms. And the limiting distribution is known as the bivariate extreme value distribution, right? Okay, so that's the story so far. So it's not all bad news, because whenever the limit exists, although it can take uncountably many different forms, you can actually determine the form of the limit if it exists, right? And to determine that, I'm going to talk about the procedure for doing that. How to determine G. G is the bivariate extreme value CDF when it exists, right? There is a 4-step procedure. The first step is to determine the marginal CDFs fx and fy of f. Remember, f is the of the data. For example, it could be the bivariate normal distribution, which I'm sure you must have done bivariate normal in some of the courses you've taken in the past. Or it could be the bivariate T distribution. It could be the bivariate Poisson, or it could be the bivariate logistic distribution, and so on. Okay. So the first step is to determine the marginal CDFs of f, right? And these marginal CDFs must be univariate CDFs because they are marginals, right? Okay. So the second step is to determine the max domain of attractions of fx and fy. And because they are univariate, because fx and fy are univariate, they must belong to one of 3 possible domain of attraction, that is either Gumpel, the Frechet, or Weibull, right? I mean, that's what we talked about in the univariate extremal types theorem, right? So if fx and fy belong to the Gumpel limit, right, then you choose the scaling constants a and b and c and d and to be this, right? And if fx and fy belong to the Frechet limit, the Frechet domain of attraction, then you choose a and b and c and d and to be this, right? And finally, you should choose if fx and fy belong to the Weibull domain of attraction, then you choose a and b and c and d and to be this. These are the formulas. All right? And you may ask, I mean, I know this is a question I get, but you may ask why they should belong to the same domain of attraction. I mean, it's also possible that fx could belong to the Gumpel domain, whereas fy could belong to Frechet domain. Yeah, but I have avoided those cases because it is possible. I mean, but in the exam, at least for this course, as far as this course is concerned, the questions that you will get in the exam and so on will belong to one of the 3 cases, A, B, or C, where both marginals, fx and fy, belong to one of the 3 domains of attractions, either Gumpel, the Frechet, or the Weibull. Okay, guys? But in practice, it's possible. In practice, you can have, one of the marginals belonging to, say, Gumpel domain of attraction, whereas the other marginals belonging to, say, Frechet domain of attraction. Yeah, but let's ignore the cases. Ignore those cases. Okay. All right. The last step for determining G is to take the limit of this power n as n goes to infinity. Okay. So this is a 4-step procedure. I'll do some examples later on, but this is a 4-step procedure for determining G when it exists. All right. Now I did some example here. This is an example. I hope you guys went through this. This is an example I did on the 4-step procedure. So the first step, as you can see, the first step is to determine the marginal CDFs of x and fx and fy, right? So this is the marginal CDF of x, and this is the marginal CDF of y. That's step number 1. Step number 2 is to determine the domain of attractions of the marginal CDF. So I'm sure we did many examples on domains of attractions in the first 2 weeks or so. First, we did many examples, right? So you should know how to do that. So in order to do that, you find the w of f of x, which turns out to be plus infinity, and then you check condition 1. Remember, this is condition 1. So if you check condition 1, it turns out, where am I? Sorry. It turns out that actually condition 1 is satisfied. Condition 1 is satisfied because, as you can see, the limit is equal to EF minus x, right? So hence, condition 1, hence the marginal CDF belongs to the Gumbel domain of attractions with the gamma function identically equal to 1, right? And similarly, because of symmetry, because the joint CDF is symmetric, you can also say by similarly that the marginal CDF of y also belongs to the Gumbel domain of attraction with the gamma y identically equal to 1. Right? So that's the second step. The third step, step number 3 is to use the formulas I gave you to determine AN, BN, CN, and DN, right? So you need to go back to the 4-step procedure. You remember the 4-step procedure. Look, you look at this. If fx and fy belongs to the Gumbel domain, then these are the formulas for AN, BN, CN, and DN. So that's what I have used here. So I have used those formulas to figure out the AN to be equal to 1, BN to be equal to log of n minus 1, Cn equal to 1, and Dn equal to log of n minus 1. So that's step number 3. Step number 4 is to find the limit. This is usually the most difficult step. Step number 4 is to find the limit of this as n approaches infinity, which turns out to be this. This turns out to be this. This goes to this, because some people ask me why this goes to this. Let me explain why. Because can you see why this is equal to this? Yeah. Come on, guys. You should have, the reason is you should have something like e of minus log of z, right? And that is equal to 1 over z. You know this, right? Or don't you? That's what I have used. So I have used this. I have used this fact to go from this line to this line. Okay. All right. And then from this you get this. I multiplied by n and divided by n, and then you go to this, right? Go to this, and then I'm going to call this guy here z, right? This whole thing in the red circle, I'm going to call it z, okay? And then you come to this, which you can write like this. Now this must be a result you must be familiar with in your 3 years of undergraduate study, or more, I don't know. The limit of this, I'm sure you know, is e of z. All right, so this is e of minus z, and this becomes, if you put z back into this, you will get this. All right, and finally, taking the limit, this becomes equal to this. So hence, the formula for g is equal to this, right? You guys have any questions, or is it? I mean, this example, these are just, again, you have to do lots of questions like this. I mean, you should go to the course website. You should go to the course website. You will see there are every past exam paper. I think there are last 6 or 7 years of past exam papers contains a question like this, right? So I suggest you just try to do them by yourself, and if you get stuck, of course you can look at the solutions, and or come and see me, or contact me 24/7. Okay, are you guys okay? Any questions on the Zoom? Guys, talk to me. Any questions you guys have? All right. So that's just one example. I will try to do more examples later on. But right now, the next thing I'm going to talk about is, all right, so we know that when the limit exists, the possible forms can be uncountably infinite. But there is some good news. There is some good news. Suppose the marginals fx and fy belong to the Gumbel domain of attraction, right? Then in this case, the possible forms for G can be expressed in this form, where f1 and f2 are non-negative functions integrating to 1. All right. So these are all the infinitely possible forms for G can be expressed in this form if these two belong to the Gumbel domain of attraction. Okay. All right. So that's good news. And the next good news is this. This is again if the marginals belong to the Gumbel domain of attraction, then the possible forms for G, of which there are infinite, uncountably infinite, can be expressed in this form, where K is a function that satisfies these 1 to 5 conditions, right? So, okay, that's number 2. Number 3 is this. If the marginals of X and Y belong to the Frechet domain of attractions, then the possible forms for G, of which there are uncountably infinite, can be expressed in this form here, where A is a function from the unit interval to the unit interval satisfying these conditions, right? And A is one of the conditions is that A must be a convex function. I'm sure you know from you should have learned this in your first year undergraduate. A function is convex if its second derivative is positive for all x, right? Okay, so that's 3. 4 is this one. It's slightly different. If the marginals of G are exponential, which means that the marginal of x must be 1. This is the CDF of a univariate exponential distribution with the parameter equal to 1, and so is this one. So in this case, the possible forms for G bar, remember G bar is the survival function of G. You may I introduced this notation some time ago, that if you put a bar on top, it means it's a survival function. Okay, so G bar can be expressed in this form, where A is once again the same function satisfying these properties. Okay, that's representation 4. And finally, an open problem for you. This you can look at this if you have time. It's not a difficult problem. Okay. Okay. So, all right. Now, next thing is I'm gonna. This is an example I did in the video. So you have this G bar given by this, right? So what you need to figure out is we talked about 4 different representations, right? 4 different representations. So what you need to figure out is which of the 4 representations this corresponds to, right? So, all right, so it always helps if you take the marginals. So you should take the marginal of this. The x marginal of this is this, and the y marginal of this is this. And both these are exponential CDFs, right? So hence, this must correspond to representation number 4, right? Okay, so the first thing you must figure out is the function a. To figure out the function a, you write this in this form, right? So your function a is equal to this, which means that a of omega is this function here. Then you must check the 4 conditions. Remember, there are 4 conditions that a function a must satisfy. The first condition is that a at 0 must be 1. The second condition is that a at 1 is 1. And the third condition is a little bit involved, because the third condition is this one here, which is the same as saying all 3 of these conditions hold. That is, a of omega is less than or equal to 1 for all omega. A of omega is greater than or equal to omega for all omega. A of omega greater than or equal to 1 minus omega for all omega. So I call this A, B, and C. And A is proved here, and B is proved over here, and C is proved over here, right? And the final, the fourth condition is that you must prove that A is a convex function. So as I said to you just a minute ago, a function is convex if second derivative is positive. So the first derivative is this, the second derivative is 2 theta, which is a positive number. Therefore, A is convex. So hence, G bar corresponds to a bivariate extreme value distribution. All right, so that's the videos I asked you to watch. Any questions, guys? No? Yes? Are you okay, guys? All right, let me do an example, right? This is an example on okay. All right, so for this kind of question, you need to use the 4-step procedure, which I talked about a while ago, right? So you know what I'm talking about when I say the 4-step procedure. Let me show you. Yeah, sorry, excuse me. This is the 4-step procedure I'm talking about, right? So the first step is to find the marginal CDFs of fx and fy. All right, so let's do that. So the marginal CDFs is Okay, and the marginal city of a y, if you cannot follow this, just give me a shout, okay? So this is step number 1. Okay, step number 2 is to determine the domain of attractions of the marginal CDFs. Now, I'm sure we've done plenty of examples. We've done many examples on which of the 3 domains do you think this belong to? You should be able to tell. Which of the 3 domains do you think it belongs to? These guys. It's clear that because x is greater than 0, the upper end point must be plus infinity, right? So I'm going to check condition number 2 because I have a feeling that it's going to belong to the Fresher domain.
That's because there's no exponential when it's like x to the power of
It's not really. Well, yeah, that's one reason, yeah. I thought you guys did enough examples to see this. When you have a polynomial power like this, it's almost always Fresher. Yeah. So when you have, I mean, this is a polynomial power, right? When you have a polynomial power, especially a negative power, you will get okay. This is what you get. Now the 1 and the 1 cancels, so this gives you the limit okay. Now what I'm going to do is I'm going to divide the top and the bottom by t. So it's going to be 1 over t plus ax, 1 over t plus a. Okay. Now as t goes to infinity, both these go to 0, so the limit is x to the power minus q. Right, so we have shown that fx belongs to Fresher domain of attraction. All right, you guys with me or what? Yeah. Okay, similarly, because of symmetry, fy also belongs to the Fresher domain. Okay. All right, so we're done with step number 2. Now step number 3 is to determine the constants a and b and d, a and b and c and d n. So if I go back to, these are the formulas I gave you earlier, right? For a and b and c and d n when fx and fy belong to the Fresher domain. All right, so basically you need to determine an, you need to set this guy equal to 1 minus 1 over n. right? And then solve for x, right? So this implies that excuse me, let me take this away. So this implies that 1 plus ax to the power minus q is 1 over n. Yeah, correct me if I'm wrong. So 1 plus ax is equal to n so x is equal to okay, so this is your an. So your an is equal to this, and your bn is your bn is 0 because that's what you're told. If you look at the formulas here, once again your bn is 0, and similarly because of symmetry your cn is divided by b, okay, and your dn is equal to 0. Okay, all right guys, so that's step number 3. Now step number 4 is the most difficult part, is to figure out the limit. Now what the question, if you look at the question, it gives you the joint survival function. So in order to figure out the limit of this as n goes to infinity, right? We need, because we don't know what f is, because we are only given f bar, not f, right? So what I'm going to do, guys, is to first write. You remember, I think it's about a couple of weeks ago, or 2 or 3 weeks ago, I gave you a relationship of f and f bar. Do you remember that or not? You do? Yeah, so you can write this in terms of f bar as the following. Sorry. Okay. Do you remember this formula? I gave it to you some time ago. Not long ago. I mean 3 weeks or so ago. Yeah. Expressing f in terms of f bar, right? Right. Now, if you put everything we know what each of these guys is, so let's do it. So it's gonna be just a minute, it's gonna be 1 plus ax 8 times your x is a n x plus b n to the power minus q, right? And then you have 1 plus b c and y plus dn to the power minus q, and then you have plus 1 plus a times an x plus bn plus b times c and y plus dn plus c times right to the power minus q. I know they look nasty, but they will simplify in a while. Just a minute. Now, if you put whatever we figured out for an and bn in the previous step, right? If you put them, you know, because we know bn and dn are 0, and we know that from the previous step that an is equal to this guy and bn equal to this guy. So if you put them together and do the math, you get, let me do the math. So it's it's possible I might get it wrong, but an is, what was an? Let's see. N was n over n to the power that. Okay. So it's gonna be 1 plus n to the power 1 over q minus 1, so the a cancels, times x to the power minus q. Then you have minus q, right? Then you have plus then correct me, then plus c times, is it a over b, I think. Squared xy. Alright guys, so I think we are running out of time, but you should do the simplifications and so on.
Why is why in the marginal survivals?
Yeah.
Why is the 1 to the power of minus q? Why doesn't it know? Isn't 1 outside of the bracket?
Oh, no,
Yeah, not the math,
no, I think it's okay. Okay. Anyway, you should simplify this. I think you can try your, I know you guys are experts in math, so you should simplify this. Because I'm running out of time, I don't think I have the time to simplify this. But you should do the limiting, your limit, I mean, this is where your limiting calculus comes in. So you should do your limiting calculus. This should, after a while, your limit must be equal to e. This is what you should get. Just try your math, guys. So this is your g of x comma y. All right. Okay, guys. So try your math. I mean, it's just simple. It's not difficult limiting calculus. I mean, it's basically everything that you learned in your first year undergraduate degree, right? So if you apply whatever you learned, you should get this down to this after a few steps. And if you have trouble, just let me know. I will help you. I think this is one of the past exam paper questions, so you can see the solution. You can see the solutions on the course website, right? Yeah, but any case, I mean, you can contact me, whatever problem you have, okay? I'll post this, are you okay, Veronica?
Yeah.
Okay, I'll post a copy of this on the course website. Alright guys, so I'll see you guys on, oh, we still have 4 minutes left. I thought my time was wrong. So what you do is, I mean, in order to simplify this, you just need to, you need to just pull this outside of the big brackets, right? So just pull this outside of the big brackets, and you will get, if you pull this outside of the big brackets, it will become 1 over n, and similarly here you will get a 1 over n times a factor, right? And here also you'll get 1 over n times a factor. And then you will use the result that I mentioned, that if you have something like 1 plus z or z divided by n to the power n, then that approaches exponential of z, right? So that's what you will. Hmm? Yeah. You have to just, all right, let me let me explain what I meant here. When you should pull out this, Veronica, outside of the brackets, right? This one. You pull this one, right, outside of over here, and similarly pull this one outside of here, and the same thing here. Pull these two guys outside. When it will become the following. Let me explain what. Let me explain. It will become 1 over n times 1, oh, sorry, times x, I think, x plus 1 minus x divided by this to the power minus q. Okay, and then you have 1 over n, can you see this here, times y plus 1 minus y divided by this to the power minus q. And then you have in the third term, or the fourth term, you will have plus 1 over n times 1 let me say 1 over n over this, yeah. Then you have x plus y, correct me if I'm wrong, but minus x over this, minus y over this, and then you have Just a minute, give me a sec. How do you take out, sorry? How I got this? Because I just, as I explained here, I pulled this outside of the bracket, right? So when it goes outside of the bracket, it becomes 1 over n. Or don't you follow that? No? Come on. Because it's like n raised to the power 1 over q, and that raised to the power minus q. So the two q's cancel out, so you get n raised to the minus 1, which is 1 over n. Then you follow? I mean, you can think about it, it's not hard. Yeah, and it's not hard. So and after, I mean, this you should do the math for this, right? You should do the math for this, and you should get the limit to be what I said the limit is gonna be. Okay, so I think let me check again. Yeah, I think this is correct. Yeah. So you should do the working out for this. This will be equal to, which is the g of x comma y. Okay. All right, guys. So let's stop it here for today. Any questions on this, feel free to contact me, all right, 24/7, and I will see you guys on Friday for the tutorial. And next week, as I said, next week is revision class, so any questions you guys, please email them to me so I can do them for next week. Okay, have a good day, guys. Good afternoon or good evening, wherever you are. I'll see you soon. There's somebody waiting for us. Don't know. It's maybe. Veronica, you can drop and see me in my office, or give me a Zoom call. I will explain to you.
Okay.